Well, in this lesson, we're going to be solving systems of linear equations in two variables. This is section 5.1. Looking at the general form of a linear equation, we have ax plus by equals c. It further states two linear equations are called a system of linear equations or a linear system. A solution to a system of linear equations in two variables is what we call an ordered pair that satisfies both equations. All right, so example 1, consider this system of linear equations. We have 2x minus 3y equals -4, and we also have the linear equation 2x plus y equals 4. And we're asked here to determine if each of these ordered pairs, 1, 2, and 7, 6, if they are a solution of the system. And the directions are, let's just plug in x and y into each equation. So for this example right here, this ordered pair, let's plug in 1 for x and 2 for y, one at a time into each of these two equations, seeing if the ordered pair 1, 2 satisfies each of them. So I'm going to grab top equation here. And where I see x, I'll plug in 1, so 2 times 1 minus, and then where I see y, I'm going to plug in 2, 3 times 2. And right here at the equal signs, I'm going to put a question mark up there, and then I'm going to record -4. I want to see if these computations will result in my getting -4. So this is 2 minus 6, and 2 minus 6 is -4. I'd put another question mark here while I'm still trying to decide. So -4 does equal -4. Well, it's not enough that the ordered pair 1, 2 satisfies the top equation. Does it also satisfy the bottom equation? Again, plug in 1 for x and 2 for y. I'm just going to put a little question mark here until I decide if this is true. Well, this is 2 plus 2, so that's just 4. And yes, 4 does equals 4. 4 equals 4. So let's just respond to the question. Yes, the ordered pair 1, 2 is a solution. All right, for example B, we want to see if the ordered pair or the 0.76 falls on both of these lines. This is x, this is y. (14 minus 18), does that equal question mark -4? So yes, -4 does equal -4. Here you might notice already this is not going to equal 4, so 14 plus 6 will not equal 4. So 20 does not equal 4. So because 7, 6 only worked in one and not both of the equations, okay, we'll respond and say no, 7, 6 is not a solution. All right, here's a graphical representation of a solution to a system of linear equations, and there's 3 possibilities. So in this first case right here, you could have 2 linear functions, 2 lines intersect in 1 point. So this is called exactly one solution. We call that a consistent and independent solution. All right, this middle case right here, you can't see 2 lines, but there are 2 lines. They just happen to be the same 2 lines, and they lay on top of each other. So are there any ordered pairs that fall on both of these lines? Well, yes. There's infinitely many solutions, so we call this a consistent and dependent solution. So when you have at least one intersection point or infinite number of intersection points, we call these systems consistent. And depending upon the situation, it might be an independent situation or it might be a dependent situation. And the third possibility is that you might have two lines that are parallel. That means that these will never intersect, so they don't share any ordered pairs. So we have no solutions, and then this system is called inconsistent. So our work here in the next few minutes is going to be to determine, given two linear equations, if we have one intersection point, infinite number, or if we have no intersection points. Okay, and what we're going to do is we're going to learn two methods to determine if we have a solution. We're going to use the method of substitution, and we'll do a few examples of that first, and then we're going to look at what we call the elimination method. Okay. All right, so for the substitution method, these are the steps that we're going to follow. I think I'm just going to jump into solving one of these problems, these systems, by using this method. So you might want to go back and look through and read through these steps, and you'll see that we did exactly follow these steps to solve this system. All right, so in example 2 here, we're going to solve by the substitution method. Well, I have the equation x plus y equals 6 and y equals 2x. So the first step is let's solve either equation for one variable. We're going to choose a variable with a coefficient of 1, and it can be x or y. So I'm just going to kind of scan the equations, and I see that this x and this y both have a coefficient of 1, but I also see in equation 2 that y has a coefficient of 1. I think I'm going to start with the bottom equation. I want to take one of the two equations and isolate the equation for either x or y on one side of the equation. Okay, so this is already solved for y, so this is really step 1. This is solved for y already. All right, so for step 2, it tells us that what we want to do is we want to substitute the expression you found in step 1 into the other equation, because this is going to create one equation in one variable. Okay, so what does that mean? We have to substitute equation 2 into equation 1. Well, I'm going to take equation 1, and wherever I see a y, I'm just going to put a parenthesis. So this is exactly equation 1, but this big parenthesis is going to represent what y is. Well, I see in equation 2 right here that y is equivalent to 2x. So I'm going to plug in where I see y here, I'm going to plug in 2x. And we just kind of think ahead, okay, this equation only has x in it. So now I'm going to go ahead and solve this equation. So that's what we're going to do next. We're going to solve for x. So I'm going to collect, and I'm going to get 3x equals 6. So x equals 2. All right, step 4 is going to ask us to back substitute. We've got x, now we need the y because we need an ordered pair. So now it doesn't matter where you plug 2 in for x. You could either plug 2 in for the x here, or you can plug 2 in for the x here and solve for y. Probably the best choice is to plug in x here since you've already got y by itself. So I'm going to choose this equation, and then down below it, wherever I see x, I'm going to replace the numeric value. So this means 2 times 2, so y is 4. So this is our solution expressed as an ordered pair. X comes before y, x was 2, and y was 4. Okay. You should probably check the solution in both of the given equations. Okay, like we did back up there in example 1. Check to make sure, but it does work. Let's do a couple more examples of the substitution method and trying to find an ordered pair that satisfies this system. So, and just thinking ahead right here, if we wanted to qualify this solution, this is going to be a system right here that's consistent and independent. All right. So for example 3, okay, again, let's solve by the substitution method. Well, okay, step 1 had us choose one of the equations and solve for x or y. So I see in the second equation that y has a coefficient of 1. So I'm going to come over here in step 1, I'm going to solve for y. I'm going to subtract 2x from both sides of the equation. So all I did was rearrange this equation for y. All right, step 2, let's substitute this equation into the top equation now. So let's write the top equation, but wherever you see y, you're going to leave a big parentheses so that we can substitute in. So y is going to be replaced with what it's equal to, which is negative 2x plus 1. Okay, in step 3, we're going to solve for the variable we see here, which is x. So let's do the algebra. So what we have to do first is, following the order of operations, you have to distribute the 2 in. So let's bring down the 3x minus 4x plus 2 equals 4. Let's clean this up. This will collect to negative 1x. Those will cancel. This is equal to 2. Divide both sides by negative 1, which just has the effect of changing the sign. So positive x equals negative 2. So we've got half of our answer. So now for step 4, let's back substitute. Okay, so now we've got to find y. So it's probably best with this strategy, if you're going to find y, go ahead and use this rearranged equation here. You could either use this top equation, this bottom equation, or this rearranged form of this bottom equation to get your y value. And no matter what, as long as we don't make mistakes, we're going to get the same y value. So I'm going to pull over this equation and evaluate it at my x value of negative 2. That's 4 plus 1, so my y value is 5. And step 5 has us write the answer as an ordered pair. X comes before y, so this is my solution. And again, this is a consistent, independent answer because we only got one answer ordered pair that satisfies this system of equations. Example 4. All right, I see in both equations that I have x isolated, so that's a good thing. I can choose either the top equation or the bottom equation to begin with. So for step 1, okay, I've already got both equations solved for x, so I guess I'll just say that one of these equations is solved for x already. There's no rearranging I have to do to get an x or y by itself, a 1x or 1y by itself. So over here for step 2, if they're both equal to x, then what I could do is I could think about taking x equals 2y minus 1 and replacing it in for this x right here. In effect, you're just setting these two equations equal to each other since they're both equal to x. Now let's solve this equation for y. I'm going to subtract this 2y since 2 is smaller than 3. Collecting downward, we get 1y plus 7. Subtract a 7 from both sides. Okay, so I've got y. Now I've got to find x. So choose either the top or the bottom equation to evaluate when y is negative 8. Just go with the top equation. Doing the work here, negative 24 plus 7 is negative 17. So I do have an answer. It's x equals negative 17 and y equals negative 8. X comes before y. So again, we only found one solution. So what that means is we have a consistent, independent system. Okay, we haven't seen yet what it looks like if we have infinitely many solutions, or we haven't seen what it looks like yet if we have no solutions, an inconsistent system. That's coming up here in a bit. All right, method 2 for solving a system. We're going to create one equation in one variable by eliminating a variable. We're going to eliminate a variable by obtaining for one of the variables coefficients that differ only in sign. And here are the steps that we're going to follow when using the elimination method, sometimes called the addition method, okay, to solve a system of equations. I think I'm going to do problem 5 last. It's actually the easiest one, and we really can't see a pattern. So let me save that for a little bit later. We can start with problem number 6. Okay, so the steps in solving the system isn't like the substitution method. What we want to do is make sure, first of all, that our two equations are in the form ax plus by equals c, where both x and y are on one side of the equation with just a constant, a number on the other. And certainly both of these equations satisfy that general form. Okay, what we want to do is we want to look at this and go, let me eliminate either the x's or the y's. And we're going to do that by multiplication and adding things together. So I'm going to kind of just first of all inspect these equations, and I'm going to look at the coefficient 3 and 4 when I look at the x terms. And I think about 3 and 4 and how if I were to add down, I would get 7x. And then over here, when I add down 2y plus 1y, I would get 3y. So right now, I don't have a situation where if I were to add these two equations together, one of the two variables would be eliminated. So I think what I'm going to do is I'm going to look at the y terms, and I'm going to look at the bottom equation, and I realize if I make the coefficient on y here -2, when I add the positive 2 down with it, okay, that those would cancel or eliminate. So what we're going to do over here is I'm going to come and say, you know what? Let me multiply this bottom equation by -2. So I'm going to take this, I'm going to see if I can get some room here. I'm going to take this bottom equation and kind of wrap it up in parentheses and tell myself, let me multiply every term in that equation by -2. I can't just decide to multiply one of the terms by something. I have to multiply all the terms by that same value. All right, so I'm going to keep the top equation. I'm not going to make any changes to it. But in this bottom equation, I'm going to distribute and multiply in a -2. So this term becomes -8x. This term becomes -2y. And always don't forget to multiply the -2 or this multiplier into the constant. So that'll be 4. Now I'm going to draw this straight line here that says I'm ready to add down. So let our eyes just kind of follow by looking at adding these two terms together. That results in -5x. When you add these two terms together, they're eliminated. Go across the equal sign, add 11 and 4, get 15. Now we can continue solving. Divide by -5, and we now know our x value is -3. Okay, so what do we do to find the y? Well, we just go back and back substitute. Let's plug -3 in for x, either in the top or bottom equation. And in this one, it just doesn't matter. So I'm going to use the top equation. And right here where x is, I'm going to replace it with -3. Let's multiply and get -9. Bring down the rest of the problem. We have an equation with just y. So now I can isolate y. So my solution is x equals -3 and y is 10. It should work out to where you get pretty nice numbers. I don't think we've created any problems here where you get ugly numbers. If you do get ugly numbers, chances are you might have made a mistake, and you might want to go back and kind of look to see where that might have happened. Let's do another elimination method, number 7, and then we'll come back and do number 5. All right. Let's look at this equation and let's see which variable we want to eliminate. Do we want to eliminate x's or y's? It doesn't matter. It doesn't matter which one you work with. You should get the same answer if we don't make a mistake. First thing my eyes look at is I look at the coefficients on y and I see that they're at least the opposite sign. So I look at 3 and 4 and I think about what is the first number, the smallest number that both 3 and 4 divide into. Well, I know 3 goes into 12 and 4 goes into 12. So let's try and make this term a 12y and this a negative 12y, so when we add down, they're eliminated. Well, how do I make 3y a 12y? I'm going to multiply the top equation by 4, because I know 4 times 3 is 12y. How do I make negative 4 a negative 12? Well, multiply by 3. Okay, so let's go ahead and do that multiplication. So multiplying, distributing 4 into all the terms of the top equation results in 8x plus 12y equals negative 24. Multiplying 3 into all the terms, I'm going to get 9x minus 12y equals 75. Straight line here, I'm ready to add down. So adding down, I'm going to get 17x, but these two terms will be eliminated, equals, and this is going to be 51. Continue solving for x. So when we go to our calculator, we get 3. Okay, which equation do you want to evaluate for x equals 3? It doesn't matter. So it looks like y is going to be negative 4. So we have one solution, the ordered pair 3, negative 4. Again, this is going to represent with one intersection of two lines a consistent independent situation. Okay, let's go back to number 5. It's also the elimination method. Okay, this was the easiest problem like I mentioned earlier, and that's because when you scan the x terms and then you scan the y terms, you can see no changes need to be made to either one of these equations. I don't need to multiply either the top or the bottom by any constant so that I could eliminate the y terms. So I'm actually just going to add down here. So 1x and 1x make 2x. The y's will be eliminated. So x equals 2. I'll just use the top equation to find y. So consistent, independent. So those are the two methods of solving a system of equations, the substitution method and the elimination, or it's also called the addition method. All right, so far all we've seen are examples of systems of equations that have one solution. So these two examples are going to be where we get no solution or an infinite number of solutions. So it says systems having no solution or infinite. We can choose to either use the substitution method or the elimination method, whichever looks to be the best method. Okay, for example 8, I probably will use the addition or the elimination method, because with the substitution method, I don't see a coefficient of 1 on any of the x or y terms. All right, so let me get my game plan here. What do I want to eliminate, x's or y's? Well, if I try to eliminate the x terms, I would need to multiply the top equation by 2, resulting in 10x to cancel or eliminate with negative 10x. I could likewise multiply negative 2y by positive 2 to get negative 4y, which when added to 4y also cancels or eliminates. So it doesn't really matter. I'm going to multiply the top equation by 2 and record it over here. Don't forget to multiply the 2 by the 4. So sometimes arrows helps to remind you to do so. So I multiply the top equation by 2. Now let me just re-record the bottom equation. Right, when I add down, the x's eliminate, but what also happens? The y's eliminate. I get 0 equals 15. We know that to be a false statement. So what happens when you get to this point? Well, there's no solution. So that means we have two lines that are parallel. So this is an inconsistent system. inconsistent. These are parallel lines. All right, we're finished. Let's move on. Okay, so for this system of equations right here, I'm trying to decide how do I want to solve these. Substitution or elimination. If I'm going to use elimination, I'm going to have to rewrite this top equation in ax plus by equals c form. That's fine, I can do it. Or I could use the substitution method, which I would use the substitution method because x is already solved by itself. It's isolated with a coefficient of 1. I'm going to use the substitution method. So I'm going to substitute in 4y minus 8 in for this x right here. So now I have an equation with just y, so let me go ahead and solve for y. So I'll distribute the 5 in. I can see over here that these two terms will cancel, and I end up with negative 40 equals negative 40. That's a true statement. Okay, so if you end up not getting any variables at all, but the two numbers are equal, okay, then this is one of our other cases. This means that we have the same line. So we have infinite solutions. This is what we call a consistent system. Same line. Okay, so when you get this weird situation when you're doing some solving by the elimination or the substitution method and you lose all your variables in your work, then look at the numbers and see what it reveals to you. If you get a false statement, okay, that means you don't have any intersection points. We have no solution. If you use one of the two strategies to solve this system and you lose all your variables, so to speak, but you get two numbers that are the same, then that's our infinite solution or same line situation, okay? All right. Okay, for this next part of the work, we're looking at a non-linear system in two variables. Well, a non-linear system means that when you look at the two equations, one of them is not a linear equation. And we can see this top equation right here. This top equation is not linear, it's quadratic. So can we solve that? Well, yeah, we could solve it by using either of the two methods. Well, actually, we'd have to solve it by using the substitution method here. Well, not actually, but I mean, that is one of them. That's a common method to use to solve this system, okay? Just as a graphical representation of what a nonlinear system might look like, if you have a quadratic equation, we would have a parabola. If you have a linear equation, you'd have a line. It's definitely possible for a line and a parabola to intersect in 2 points. It's also possible in another case to have a parabola, maybe something like this, and a line, something like this, where we have no solution. Another case might be you might have a parabola, you might have a linear function, but it only intersects the parabola in 1 point. So there's a lot of different possibilities with a nonlinear system as well. So this is all worked out on the key. I'm going to leave this for you to solve and, look at the key to assist in that. All right, I want to look at one last application problem here. So give you kind of a minute to kind of look over that. Okay, so what's an application of solving a linear system? Well, we have revenue and cost functions. Let's say that a company sells X units of a product. So what's our revenue function? Well, we'll use uppercase R in terms of X, the X units of a product, and it's how much they sell their product for times X. What's the cost to the company? Well, any fixed cost they have, like their lease or their rental or their equipment cost, plus what does it cost to produce each unit? So that's the cost times each X unit. And what's the profit function? Well, the profit function is going to be your revenue minus your costs. And here's a graphical representation of what that might look like. So for this example right down here, we have a company that manufactures running shoes that has a fixed cost of $300,000. Maybe that's the rent on their building or their equipment. Then additionally, it costs $30 to produce each pair of shoes, and then they're turned around and sold at $80 per pair. Let's make sure that we know what to define our variables, that X is going to be a pair of shoes, one pair of shoes. So they want us to write the cost function of producing running shoes. So the cost to the company in terms of the number of pairs of running shoes they sell is equal to their fixed costs, $300,000, plus it told us that it costs $30 per pair to make, so 30 times X. So I could have rearranged this and put 30X first. Okay, it doesn't matter the order. Okay, they want us to write the revenue function from the sale of X pairs of running shoes. So the revenue function as defined up there, the top, they're going to make $80 per pair of shoes. All right, let's determine the break-even point. When are they finally going to start making money? And that's where these two equations are equal to each other. So when does the revenue equation equal the cost equation? All right, to mathematically solve this, let's get X by itself. All right, so my answer is 6,000. So what does 6,000 mean? It means that any pairs of shoes over 6,000 that they produce, they're going to start earning a profit. And that's solving systems of linear equations.